Welcome back. We are at chapter 17.4, textbook page 441. Yeah, equation of motion, rotational about fixed axis. Yeah, so the application is there are a lot of applications. So one of it is like the crank oil pump brake undergoes rotation of the fixed axis caused by the driving torque from the motor. Okay, so if you see this, the pin center here, this thing is actually rotating. Yeah, it's rotating. So as a crank turns, a dynamic reaction is produced by the pin. So this reaction is function of angular velocity and angular acceleration. Okay, next example is this Choppy machine. You have seen this in the lab. Some of you have done this experiment before. If you see, this arm actually rotates. Yeah, so you can actually calculate whatever that's asked by this question at the end of this chapter. Okay, so let's look at this. We have series of formula. One is this f. Okay, earlier it was fx, fy, right? Now it's fn and ft, because this is actually curvilinear movement while it's rotating. Earlier was linear movement while it was rotating. Now curvilinear movement while it's rotating. So that's why you have Fn and Ft. Yeah. Okay. Okay. What about if? If let's say, now this is if the whole thing is at point G at the mass center, right? So need not all time that it will be at point G. Sometimes it can be point O. So what does it mean by if it's point O? It's another, you have to apply the parallel axis theorem. Remember earlier we did that? Yeah. So m naught will be Ig plus with the distance multiplied, yeah, which is actually equivalent to you remember earlier parallel axis theorem we did beta I naught equals to Ig plus mb square, right? Okay, the previous chapter. So now in this case, if let's say it is actually not at point O, not at point G, not at the mass center, but it's at point O, shifted. So what happens is that the equation is a bit altered, yeah, where you have to follow this for the moment. You have to follow this equation. See this? Yeah. Okay. So it will be Ig plus mr square, mr square alpha. Okay, so it's a bit shifted. Okay, so don't worry much about it. We will, when we do the question, you will see. So procedure for analysis as usual, you initial coordinate system, then you have to draw the free body diagram to show the forces and also the movement, and then you compute the mass for your Ig and I naught. Sometimes they give you the radius of gyration, so it's a bit easy. Next you write your three equation of motion, your fx, fy, or your moment, or sometimes it can be fn, ft, or moment depending on the question itself. Then you use your kinematics to find the unknown. So this is an example in the slides which I'm going to actually skip. Yeah, I'm going to go into example 17.9 from the textbook. Yeah, 17.9 from the textbook. This is 17.9. Yeah, so example 17.9 is actually from page 445 of the textbook. Okay, so at an instance shown, the 20 kilogram slender rod. So this rod has got a weight, yeah, 20 kilogram weight, okay, has an angular of 5 radian per second. Okay, determine the angular acceleration. So they want the alpha. Okay, and then they want what? Horizontal and vertical components of the reaction pin. So they want O. In this case, we are taking T, yeah? Fn and Ft. So it will be OT and ON. So these are the reaction pin. You remember pin from the statics lecture? Yeah, you have got two unknowns, right? Fx and Fy, so same. Yeah, okay, let's solve this question. So first thing to do is to, of course, define your axis. So you have defined your axis, you have n and t in this case, yeah, n and t. So that's done. So you draw the free body diagram. Yeah, this is the free body diagram to show all the forces, because this is a pin. So we have O and OT, and then we have weight concentrating right in the middle, and then you have moment. This moment is given in the question, so do not delete anything, just follow as it is. Yeah, and then it's equivalent to the movement diagram. Can you see movement? You have m theta rg, m omega square rg. So what is this? This is your an, and this is your at. Okay, and then you have got your moment of inertia as well here. Okay, now let's look at the formula. Fn, what are the forces for normal? So for normal, only here, one only. Yeah, one only. So for this fella, in n direction, it's only this. Yeah, only that. So it's 20. The rod is 20. Omega square is actually 5 given in the question, and the r is 1.5. Now the r is actually 3 meters. Given in the question, it is 3 meters. Why are you taking 1.5? Because the mass center is actually half the distance. So that's why rg is 1.5. Yeah. Okay. Now we're going to solve the second part, which is for the t. We are done with the r. With the n, we're going to go for the t. So ft equals to m alpha rg. So what is the ft here? We have 1, we have 2. Okay, so 1 and then 2, and then we have this. Okay, so we have m alpha rg. So alpha is unknown, yeah. So we have got 2 unknowns here. So leave this as equation 1. Okay, and then we do the same thing with for your mg. Mg is ig alpha. Yeah, ig alpha. So what is the moment? So moment at point G. So take point G as your, up here. Okay, once again. This is the G. Okay, force times distance, and then this one of course nothing, because it's running on the same line. Yeah, so OT times 5, 1.5, and then we have got existing 60. So this is actually okay. The unique part of this is that you see force times distance. If it's clockwise, it's taken as positive. It's taken as positive. So whatever that's given, like in this case it is negative, right? Around G. If it goes around G, wait 1 second, this is moment at G. Moment at G, we have OT multiply this, we have positive, because the reference is positive, so it's positive. And then in this case it will be the opposite, because this 60 is actually going this side, isn't it? Yeah, it's actually going this side, which is anti-clockwise 4.0. So we will take it as the opposite. It's supposed to be negative, but we will take it as positive because it's opposite. Yeah. So what we have here is that IG. This is a rod. So for rod, remember we go back to these. Rod axis XX because it's in the middle. So beta. Let me just look at the question. Is this right in the middle? Yeah, right in the middle. Okay, then you go back to this. This is the axis right in the middle. It's XX, so it's 1 over 12 ml square. Go back to the question. 1 over 12 ml square multiplied with alpha. Okay, so what we have here, what is the length? 3m is 20. Okay, done. So with this you can actually solve simultaneously. You get all these answers. Okay, so we are done with the first part. This is an alternative method where actually they are taking the moment at point O. Instead of G, they're looking at point O. Yeah, there's actually two working here. You can just try it out by yourself, but I prefer you to don't combine and solve like this method and this method. I want you to break it down one by one and solve it. Yeah, okay, now let's move on to lecture. So what we have here, the next part would be equation of motion, general plane motion, which is from the textbook page 456, page 456, and this is 17.5. Okay, at the end of the day, student will be able to analyze the planar kinetics of the rigid body undergoing general plane motion. So earlier we were just doing one thing at a time, or maybe two things at a time, but now we're going to be having combination of several movements together. Yeah. Okay, a soil compactor accelerates forward and the front roller experiences general plane motion. Because you have a friction, you have a normal force, and then you have a rotational as well. So because both translation and rotation, so it's a combination. How would you find the loads? Yeah, so that's why you need to study this. So first thing to draw is your free body diagram, and then this is your motion, your kinetics. Yeah, and then many examples, anything that's revolving of a what do you call rotating, and also moving in a straight line or moving in a curvilinear line. Yeah, there are lots of application. Even impact during crash, your vehicle crash. Yeah, if you don't wear your seat belt, then you're gonna have a big problem. Yeah, so that's the reason why you need to wear your seat belt and also have some airbag in your car. So let's look at this. When a rigid body is subjected to external forces and coupled moments, it can undergo both translation and rotation. Just now we were breaking down. We say curvilinear plus rotation. The first part we say linear plus rotation. Okay, now combine. Yeah, so that's why it's general plane motion, but whatever it is, it's in two axes. Yeah, xy axis. Yeah, xy axis. Okay, so this is the formula. So if you look at this formula, we have fx and we have fy, and then we have mg. Yeah, it comes in a package. Now remember, if g means they are taking the mass center, sometimes it may not be the mass center, it can be also point O. Yeah, okay, remember the previous class that we did. Okay, okay, sometimes it may be convenient to write the moment of equation in the point P. See, that's what I told you. It's not G, but it is at P. Okay, it's shifted. Okay, but we still can calculate. Okay. Okay. Okay, we will just go to the procedure for analysis. Establish xy, and then you specify the direction and sense of acceleration. You have to draw the free body diagram. Yeah, don't forget. Yeah. Okay, then only you specify. Then you solve for the equation of moment equation. Yeah. So if you see this, a continuation of the procedure for analysis, all this. Identify the unknowns, use the kinematic equations. Yeah, you have to check the validity. Yeah. Okay, key point to consider, you must be consistent with the direction. If you've taken direction x as positive this side, make sure that all throughout it is the same. Okay, that's very important. So examples in the slides I will just skip. I'll just go directly to the example in the textbook. Okay, example 13.3. Example 17.3, sorry. 17.3 is from textbook page 459. Yeah, page 459. Okay, we have the 25 kilogram wheel has a radius of gyration of kg equal to 0.2. If the 50 Newton meter moment couple is applied in the wheel, determine the acceleration at the mass center. So they want the acceleration at the mass center of G. Yeah? The coefficient of static and kinetic friction of the wheel are statics and kinetic respectively. So we have got 50 existing, we have got this, okay, we have got the distance. No, okay, now let's first step. So what, okay, determine the acceleration at the mass center. Yeah, acceleration at the mass center. They're interested to look at the AG. Yeah, AG. Okay, let's look at the working. So first step would be to find the IG. This is a jackpot question because the radius of gyration is actually given. Yeah, so IG will be mk square. Don't have to look at any reference, just take, and then this is the IG settled. Okay, this is your free body diagram and this is your motion diagram. So from your free body diagram, you know that in x direction we only have one force here, which is equals to ma, because a has got a movement. And then for y direction we have 1, we have 2, So two forces equivalent to 0. Okay, and then now we are taking moment in G. So moment at point G. So moment at point G, how to calculate? G, force times distance, 0.36. Force times distance, 0.36. There's an existing 50. There is an existing 50. Okay, just follow through. And then we have, okay, look at this, yeah. Direction as clockwise is positive. So which means 50 is in the same direction. So you just have to take it as positive. And then this one times with 0.36 will be negative because it's going this side. Yeah, and then we have IG. I you have calculated. Alpha you don't know. This is what you put in here. So when you solve this simultaneously, no, you cannot solve simultaneously. Too many unknowns. Okay, you need to find another one. So if you look here, remember from the formula of A equals to VR. Yeah, so A equals to VR. You've got 4 equations to solve for 4 unknowns. Okay, then you can solve for your NA, FA, alpha and AG. Okay, so the solution requires no slipping occurs because FA is lesser than mu and A. So since that 106, yeah, 106 is lesser than 73, sorry, is greater than 73.6. So the wheel slips as it rolls. So there is a movement, but it will be slipping as it rolls. What is slipping? Slipping means to move this way, like that. It just like sort of like a drag like that. Yeah, that's slipping. Okay. Okay. So we are done. You can also calculate the friction. Yeah, and check the answer also. Okay. So with that, we are ended chapter 17. Yeah, any questions, you meet me at the any part that you don't understand, you can just meet me at the online consultation hours, and we can always go through it again. Yeah, thank you.